Okay, in this presentation we're going to look at repeated sampling, sampling distributions, and the central limit theorem and normal approximations and stuff like that. So essentially I'll just sort of stick with the question in hand and won't go too much more into the details there. A computer routine selects one of the integers 1, 2, 3, 4, and 5 at random and replicates the process 100 times. Now, essentially what we're going to sort of state here is that this is discrete uniform because a discrete uniform distribution, uh, essentially where you're not given any information about the probability, and we just have to sort of assume that is the case. Otherwise, we wouldn't be answering this question, asking this question, or answering it in this particular video anyway. But that is, so just actually to sort of recognize that fact. Let S denote the sum of the numbers selected. So just actually quick remark on that. N is equal to 100. And calculate an approximate probability that the S assumes a value between 280 and 320. So if you run this process each time, the 2, 4, 1, 3, and so on, and add up all the numbers, you should get a number close to 320. Okay, or sorry, 300, which is the expected value of this, not that we're asking it here. Just as a remark, we're also told calculate the approximate probability that S assumes at this value. Essentially what we should do here is actually justify the normal approximation and the central limit theorem based on the large sample. So essentially you just have a little 1 or 2 line paragraph just to sort of dovetail this, just to sort of set this up, and just provide this justification, just to get the perfect answer there, as best an answer as you can. Also, what we're told here is assuming a value of 280 and 320 inclusive. Now, so that's asking us for a probability of 280 less than or equal to S less than or equal to 320. Okay. Now, if we were to break that up a little bit more, probability of S being greater than 280, essentially piece it up, and well, actually, that's that's a different event there, and S less than or equal to 320. Okay, sorry, what I'm getting at there is it's very important to know these correction factors and what to do. Okay, so essentially what I'm getting at here actually is that what to do in both cases. Okay, so we have S is greater than or equal to 280. So essentially what we're going to do here is use this one, and then S is less than or equal to 320. So when we use our normal approximation, we use the following correction factors. Okay, essentially just to sort of bear in mind what's going to happen down the line with our correction factors. You should expect these correction factors to pop up every so often when you do these sort of approximations. Right. Okay, so just actually the probability density function of the discrete, well actually probably mass function actually in this case. This is I sort of switched this from a uniform or continuous distribution. But anyway, really it is the key thing here is these things here. Okay, that's actually not entirely correct. That's for a continuous, but it's a little bit beside the point. So the mean is a over b. Mean of 1/2 times a plus b. A here is the minimum, and in this case is 1. Oops, didn't mean to do that. A here is 1. B here is 5. Okay. And so the mean is obviously the 3. Okay, mean is 3. On average, the expected value of x. Now, the variance is for a discrete uniform distribution. I did not get this wrong. Okay, it's a minus b plus 1 squared minus 1 all over 12. And that is slightly different from the continuous uniform distribution. So just watch out for that. Okay, actually, really the important thing I've done here is this part here. Okay, just to sort of note that the variance is 5 minus 1 plus 1, so it's 5 squared minus 1 over 12. That gives us 25 minus 1 over 12. Whoops. Over 12. And that is equal to 2. Okay? So the variance is going to be, the mean is equal to 3, the variance is equal to 2. So for S, the variance is just going to, for the S, which is the sum of the 100 values there, S is going to be 3 times 100. So we got 300 here. And the variance is going to be 2 times 100, which is 200. Okay? Now, actually, just as a remark, I sort of skipped over the CLT stuff here, but put in the CLT justification. Okay? And some videos I do it, some videos I don't. I just sort of do it to save time and space and so on. But anyway, the mean is 12. Sorry, the mean is 3. The variance is 2. That means for S, we're assuming that S is normally distributed with a mean of 300 and a standard deviation of, sorry, a variance of 200. Okay. Now, we're adapting from discrete to continuous. Okay? So that's where these correction factors come in. Okay? And why does it go from 280 to 279? And why does it go from 320 to 320.5? So that's it in both cases. So this is 280 to 279.5, and 320 goes to 320.5. Okay, just I highlighted that earlier. Okay. Now, so in this case, we get the z-score, and in both cases, the z-score should work out to be 1.450, or plus or minus 1.450. So essentially, once we get here, in both cases, we work out our z-score, and we get this interval here, okay, and it's a symmetric interval. So essentially, what we need to do is calculate the probability of z being greater than 1.45, and then just work it out, and we should end up with this value here. So it's 1 minus twice that, okay, as a symmetric interval. Sorry, I'm using, should just be consistent with what I used before. Okay, so essentially it's a symmetric interval, so you can re-express it as follows: 1 minus 2 times the probability of z being greater than 1.45. Okay, and that means you should get a number close to about 0.07 something. And when you work it out, you should get an answer. Overall, your answer should be work out to be 0.853. Okay, the z-score stuff should not be too much trouble. Really, the symmetric interval and all that, if you should have really be au fait with that already, and you should be comfortable with that already. That's not really the point of this. The point really here is correction factors, the mean and variance of a discrete uniform random variable, and just sort of piecing it all together. And also, don't forget that bit. I sort of skipped over it a bit, but that doesn't mean you should. Two or three lines at least. Well, 2 or 3 lines should be right, okay? Okay, let's leave it there.